So our program was called Covariant Methodology in Transformational Acoustics, and I'm Martin McCall. At the time, the student working on the project was Alberto Favaro, although he's recently successfully defended his thesis. Paul Kinslow, the postdoc in my group, and Lucy collaborated, and Santo is the local coordinator. And so just to summarise in pictorial terms what Lucy has just covered, we can imagine some abstract space or manifold in which points are redistributed and in which physical quantities, correctly or incorrectly, are redistributed in this way. And the key question that we ask is how to modify a medium so that the relocation of physical quantities actually occurs, and so in pictorial terms that straight lines become some useful curves. And as Sante said at the beginning, this transformational approach has encountered some success over recent years. This is an experiment from 2006. David Smith's group at University of Southern California originally, but I think we moved from there. I can't remember his currency institution. And this is an electromagnetic cloak. So this is a microwave experiment and underlies although the transformation is very simple, just a radial transformation, the actual medium parameters are rather complicated and in fact could only be partially achieved experimentally. So it's a kind of an epsilon and a mu that is both radially inhomogeneous and locally anisotropic. But nevertheless, there's some degree of cloaking was achieved. This is in fact a theoretical result, and this is the result without the cloak being present, and this is the experimental result with the cloak present. So you can see the partial restoration of plane waves. It's not perfect, but it works. It serves as a demonstration, and of course many of these ideas have been developed and improved since that time. My own group, in fact, has worked on development on cloaking that relates to space-time invariance of Maxwell's equation, so that this cloaking of a particular region of space can be reinterpreted as the cloaking of certain events in a space-time diagram. And so for the research in my group, came to the fore a couple of years ago in the idea of the so-called space-time cloak, or the idea that one could edit history because certain events are never concealed from observers, that never see them occurring. So the key features that Lucy has already outlined for electromagnetism are that we exploit form invariance of Maxwell's equations. And so the requirement that Maxwell's equations look the same after transformation, let's call it a morphism, which in some sense de-emphasizes the coordinate dependence aspect. The idea of morphing points on a manifold is also quite good. This morphism dictates the required anisotropy and inhomogeneity of the medium, and there's already been emphasized that for electromagnetism the method is exact. So that means that field attributes such as near field, far field, polarization, etc., are all inherited in the transformational scheme that map to new locations. And underlying this is the form invariance of Maxwell's equations. And as we found out in more detail in the project, the role of the metric appears to be fundamental. The fact that Maxwell's equations are pre-metric, whereas acoustics is not. And so that brings us to the sort of basic question that we sought to address from the outset, was can we write the basic equations acoustics in a similarly form invariant way, and if yes, then we're done. But of course the answer is much more complicated. So the answer is no. Metric fundamentally enters into acoustic equations. Then can we introduce various restrictions that enable us to make some general statements? And are there any other interesting special cases that we can identify? So we set ourselves some relatively modest theoretical goals, and we've made free use of ideas from differential geometry, covariant derivatives that are intrinsic to the underlying space rather than coordinate based, and we wish to proceed as far as possible without a metric. Ultimately, we would want to be able to design cloaks and deflectors, so perhaps some sort of acoustic liner for the aerospace industry that can deflect acoustic energy away from the ground. Although our project led somewhat towards the designs of these things, it didn't get down to the detailed engineering level, and so we were concerned primarily with conceptual issues. And just to summarise in a very quick way, because this will be dealt with more in the main presentation, these are the key outputs from our project. There turns out to be a special case called the inertial limit for the acoustic equations, in which the elasticity tensor takes a very simple form, but the mass density can be anisotropic, and we achieved a transformational, an exact transformational acoustic scheme for that case. This was extended to a class of media called pentamode media, which the next level of complexity up from the simplest elasticity tensor. That's a special medium that can support 5 shearing modes. And I should identify the names that are associated with these sub-activities. And it was really Lucy and Alberto that worked extensively on these 2 points, and that's what Lucy will explain in the main presentation. My own contribution, which I'll explain at the beginning of the main presentation, was to abandon the idea of an exact transformational scheme, but to focus rather on a ray scheme that works, that is necessarily imperfect, but appears to be quite general, and to see if there is a way that we can map some desired transformation of rays that operate at that geometrical level to some simple recipe for changing the medium. A final section of our report, which was examined by Paul Kinsler, took a very preliminary look at some algebraic cosmetics that attempted to make acoustics look like covariant electromagnetism, but Paul isn't here today, so the main presentation will cover these 3 outcomes in more detail. Okay, thank you.